We now study counting, and we start with an example. So teams A and B are to play each other repeatedly until one wins 2 games in a row, or one wins a total of 3 games. How many ways can this tournament play out? So the easiest way to determine this is to use what's known as a possibility tree. We'll start here. So this is our starting point. Now, at the starting point, there are 2 outcomes. We could have Team A win, or we could have Team B winning. If we look at the path for Team A, there are 2 outcomes. Team A could win, or Team B could win. If Team A wins, then the tournament is over. Team A has won 2 in a row. Now, if Team B wins, there are 2 outcomes. Team A wins. Team B wins. If Team B wins this time, then the tournament is over. Team B has won 2 in a row. If Team A wins, there are 2 possible outcomes. Team A could win, or Team B could win. If Team A wins, then Team A has won 2 in a row, and the tournament is over. If Team B wins, there are 2 possible outcomes. Team A could win, or Team B could win. If Team A wins, then the tournament would be over. Team A would have won 3 games. If Team B wins, then the tournament is over. Team B would have won 2 in a row. So that takes care of if Team A wins the first game. If Team B wins the first game, there are 2 outcomes. Team A wins. Team B wins. If Team B wins, the tournament is over. Team B would have won 2 in a row. If Team A wins, there are 2 outcomes. Team A wins, or Team B wins. If A wins, then A would have won 2 in a row. The tournament is over. If B wins, there are 2 outcomes. A wins, or B wins. If B wins, the tournament is over. B would have won 2 in a row. If A wins, there are 2 outcomes. A wins, or B wins. If A wins, the tournament is over. A has won 2 in a row. If B wins, the tournament is over. B would have won 3 games. So to determine how many, let's take a look. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 possible ways this tournament can play out. If we were to list them, we can list them this way. A wins 2 in a row. And we could have A wins, B wins, B wins. Then we could have A wins, B wins, A wins, A wins. We could have A wins, B wins, A wins, B wins, A wins. We could have A wins, B wins, A wins, B wins, B wins. That takes care of A winning the first game. That's this branch up here. If B wins the first game, it could be BB. Then we could have B, A. Then we could have B, AB. Then we could have, I'm sorry, BAB is not a possibility. We could have BABB. We could have BAB. AB. And finally, we could have B, A, B, A. So these are all 10 possible outcomes for this tournament. Now let's consider the following scenario. Suppose a computer installation has 4 input-output units. They are A, B, C, or D, and it has 3 central processing units, X, Y, and Z. Now, any input-output unit can be paired with any central processing unit. How many ways are there to pair an input-output unit with a central processing unit? So, to determine this, we consider this process in 2 steps. This is a 2-step process. First, we choose the input and output unit. Then, we choose the central processing unit that goes with it. If we do this, we'll get this possibility tree. Right? Step 1, choose the input-output. We could do A, and then from there we have 3 possibilities, X, Y, Z. We could do B, and then from there we have 3 possibilities, X, Y, Z. C, 3 possibilities, X, Y, Z, and then D, 3 possibilities, X, Y, Z. So step 1, we have 4 choices. All right? So in step 1, there are 3 outcomes. Step 2, there are also 3 outcomes. Step 3, there are also 3 outcomes. Step 4, there are also 3 outcomes. If we add all these together, we get a total of 12 outcomes. So this would seem to give us an idea of how many ways this operation can be performed. An operation consists of k steps, and the first step can be performed in n1 ways, the second step can be performed in n2 ways, so on and so forth. The k step can be performed in k2 ways. Then the entire operation can be performed in 1 times n2 times nk ways. Now, suppose that there's only a single step in the operation that can be performed in n1 ways. Then the entire operation can be performed in n1 ways. Now suppose that there are 2 steps in an operation, where the first step can be performed in n1 ways, and the second can be performed in n2 ways. Then each of the n1 ways of performing the first step can be paired with one of the n2 ways of performing the second step. Thus, the total number of ways to perform the entire operation is n2 plus n2 plus n2, and there are n1 of these n2 terms. Well, that's just n1 times n2. Now let I be an integer such that I is greater than or equal to 2, and suppose that the operation consists of I steps, where the first step can be performed in n1 ways, the second step in n2 ways, so on and so forth, and the ith step in I ways. Furthermore, let's assume that this total operation can be performed in n1 times n2, so on and so forth, times ni ways. Now consider an operation that consists of I plus 1 steps, where the first step can be performed in n1 ways, the second in n2, so on and so forth, the ith in ni ways, and the I plus first in n I plus 1 ways. What we have to do is show that this total operation can be performed in n1 times n2, so on and so forth, times ni plus 1 ways. Now we can think of this new process, this one right here, as a two-step process. The first step is an I-step operation that consists of the first I steps, and then the second step is the I plus first step. Now, by the inductive hypothesis, this new first step can be performed in n1 times n2, so on and so forth, times ni ways. And by assumption, the new second step can be performed in ni plus 1 ways. Therefore, by the same argument used to establish the k equals 2 case, the entire operation can be performed in the number of ways the first step can be performed times the number of ways the second step can be performed. And so we get n1 times 2, so on and so forth, times ni plus 1 ways. This is what was to be shown, and so the proof is complete. So a way to count this type of process is to multiply the number of ways the first step can be performed with the number of ways the second step can be performed with the ways the third step can be performed, so on and so forth. Now, a certain personal identification number known as a PIN is required to be a sequence of any 4 symbols chosen from the 26 uppercase letters in the Roman alphabet, I don't know why it's remained, and the 10 digits. So the question is, how many different pins are possible if repetition of symbols is allowed, and how many if repetition is not allowed? Well, if we look at repetition allowed, so it has to be a sequence of 4 symbols. So let's draw 4 spaces, right? Now, how many choices do we have for this first symbol? Well, there's 36 of them, right? The 26 uppercase letters and the 10 digits. Now, since repetition is allowed, you also have 36 choices for the second symbol, you have 36 choices for the third, and you have 36 choices for the fourth. So total would be 36 to the 4th power, and this is 1,679,616. So with repetition allowed, there's a total of 1,679,616 unique PIN numbers possible. Now, what if repetition is not allowed? Well, there's still 4 symbols we have to choose. We still have 36 choices for the first, but now repetition is not allowed. So the second one, we have 1 less to choose from. The third, we now have 1 more less, and the fourth is another 1 less. So this is 36 times 35 times 34 times 33, and this is 1,413,720. So without repetition, there's 1,413,720 unique pins that can be created. Let's now consider the following problem. By the way, this was known as the multiplication rule. I didn't explicitly state it at the beginning, but this is the multiplication rule. I should have stated it. All right, so let's consider the following problem. 3 officers, a president, a treasurer, and a secretary, are to be chosen from among 4 people: Anne, Bob, Sid, and Dan. Suppose that for various reasons, Anne cannot be president, and either Sid or Dan must be secretary. How many ways can the officer be chosen? Now, it might be tempting to argue that there are 3 choices for president, 3 choices for treasurer, and 2 choices for a secretary, making 18 total possible ways. However, this would be incorrect, because the number of ways to choose the secretary varies depending on who is selected for president and treasurer. Right? Because remember, Sid or Dan must be a secretary, and Anne cannot be president. So the easiest way, or the clearest way to see the total number of possibilities here is to create a possibility tree like we did in the opening example. And this would be the possibility tree. Right? They broke it into 3 steps: choose a president, then choose treasurer, and choose the secretary. Right? So if Bob is chosen as president, then there are 3 choices for treasurer: Anne, Sid, or Dan. Once Anne is chosen as treasurer, you then have 2 possibilities for secretary: Sid and Dan. However, if Sid is chosen as treasurer, then Dan must be the secretary. And if Dan is chosen as treasurer, then Sid must be chosen as secretary. Right? So on and so forth. So from here we can see there's what? There's 1, 2, 3, 4, 5, 6, 7, 8 total ways that this can be chosen. However, we can choose a clever order of selecting candidates that would allow for the multiplication rule. So if we decide to select secretary first, then the president, then the treasurer, we would have the following analysis. There are 2 ways to select the treasurer: Sid or Dan. Once that's taken care of, there are then 2 ways to select the president. Neither Anne nor the candidate that was chosen for treasurer can be selected. Finally, there are 2 ways to select the secretary. Neither the one selected for treasurer nor the one selected for president. This gives a total of 2 times 2 times 8. 2 times 2 times 2, which is 8 total possibilities, which is what the possibility tree gave us. Before we continue on with counting, we have to introduce a new notation known as the factorial notation. So for each positive n, this should be positive integer n. The quantity n factorial, which is denoted n with an exclamation point, is defined to be the product of all integers from 1 to n. That is, n factorial is the product I equals 1 to n of I. Furthermore, we define 0 factorial to be 1. Now, this may not make much sense at first. However, we will soon see that it is convenient for mathematical calculations. And if you get into more advanced studies of mathematics, there is a function known as the gamma function, and that can be used to actually verify 0 factorial being 1. Alright, so we're going to work with some factorials right now. We're going to simplify these following. So we'll simplify a factorial, then we'll simplify 5 factorial to 2 factorial times 3 factorial, so on and so forth. Alright, so let's start with 8 factorial over 7 factorial. Well, by definition of factorial, right, we can write 8 factorial as 8 times 7 times 6 times 5 times 4 times 3 times 2. But that is 8 times 7 factorial. The 7 factorials will then cancel out, and we're left with simply 8. If we now look at 5 factorial over 2 factorial times 3 factorial, we can write 5 factorial as 5 times 4 times 3 factorial all over 2 factorial times 3 factorial. Now our 3 factorials will cancel out. We'll be left with 5 times 4 over 2 factorial, just 2 times 1. And so we get 5 times 2, or just 10. If we now look at 1 over 2 factorial times 4 factorial plus 1 over 3 factorial times 3 factorial, we can write this as 3 factorial times 3 factorial plus factorial times 4 factorial all over 2 factorial times 4 factorial times 3 factorial times 3 factorial. From the numerator, we can factor out a 3 factorial, and we'll be left with 3 factorial plus 2 factorial times 4. Now one of those 3 factorials will cancel out, and from the numerator we can also factor out a 2 factorial. We'll be left with 3 plus 4. That will simplify to 3 plus 4 over 3 factorial times 4 factorial. We can simplify, I'm sorry, we cannot simplify any further, so this will be 3 plus 4 is 7. Now if we look, 3 factorial is 6. 4 factorial would be 6 times 4, which is 24. So we get 7 over 144. If we now look at n plus 1 factorial over n factorial, this is very similar to the 8 factorial of 7 factorial. N plus 1 factorial is n plus 1 times n factorial all over n factorial, and we're left with simply n plus 1. And finally, if we look at n factorial over n minus 3 factorial, this is a similar argument. The numerator is n times n minus 1 times n minus 2 times n minus 3 factorial all over the n minus 3 factorial. And so this is n times n minus 1 times n minus 2. Now, a permutation of a set of objects is an ordering of the objects in a row. Given a set of n objects, how many permutations does the set have? Now we can think of this as n steps. I don't know why tips is written there. Choose the first element, then choose the second element, so on and so forth, until you choose the final element. Thinking of it this way, there are n choices for the first element, n minus 1 choices for the second element, so on and so forth, and then you have 1 choice for the final element. So you have n times n minus 1, so on and so forth, down times 1, which is n factorial total permutations. Right, and this leads us to this. For any integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. Now let's consider the word computer. How many ways can the letters in this word be arranged in a row? Then how many ways can letters be arranged if CO must remain next to each other? So if we look at the word computer, there are 8 letters. 1, 2, 3, 4, 5, 6, 7, 8. So you would have 8 factorial ways that the letters can be arranged, and 8 factorial is 40,320. So there's 40,320 total ways the letters can be arranged. Now, if the letters CO must remain next to each other, then there would only be 7 letters, right? There's 7 units. We think of CO as a single unit. So there'd be 1, 2, 3, 4, 5, 6, 7. So there are 7 factorial, which is 5,040 total ways the letters can now be arranged. So an R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. The number of R permutations of a set of n elements is the note P of n comma R, or more commonly NPR. If n and R are integers and 1 is less than or equal to R, which is less than or equal to n, then the number of R permutations of a set of n elements is given by this formula, n factorial over the quantity of n minus R factorial. So let's go ahead and evaluate 5p2. So 5p2 is 5 factorial over 5 minus 2 factorial. So we get 5 factorial over 3 factorial, which is just 5 times 4, and we get 20. How many 4 permutations are there of a set of 7 objects? How many 5 permutations are there of a set of 5? So for the number of 4 permutations of a set of 7, we want to calculate 7p4. So this is 7 factorial over 7 minus 4 factorial. So we have 7 factorial over 3 factorial, which is 7 times 6 times 5 times 4. This is 840. For the set of, or for how many 5 permutations of a set of 5 objects, we are looking for 5p5, which is 5 factorial over 5 minus 5 factorial. So it's 5 factorial over 0 factorial. And remember, 0 factorial by definition is 1, so this is just 5 factorial, which is 120. How many different ways can 3 of the letters of the word bites be chosen and written in a row? How many different ways can this be done if the first letter must be B? Well, if we look at bites, it has 5 letters. So what we're looking for is the number of ways 3 of these letters can be chosen and written in a row. So we're looking for the number of 3 permutations in a set of 5. So we're looking for 5p3. 5p3 winds up being 60. Now, if the first letter must be B, then there are 2 more positions with 4 letters to pick from. So now we have a set of 4 and we want to pick 2 letters. So we're looking for the number of 2 permutations out of a set of 4. So we're looking for 4p2, and this is 12. So there are 60 different ways. 3 of the letters of the words bytes can be chosen and written in a row. And there are 12 different ways this can be done if the first letter must be B. But now, just an interesting property of permutations, just to work with them. For every integer n greater than 2, np2 plus np1 is equal to n squared. So suppose that n is an integer such that n is greater than or equal to 2. Then np2 plus np1 would be n factorial over n2 factorial plus n factorial over n minus 1 factorial. So we can write this as n times n minus 1 times n minus 2 factorial all over n minus 2 factorial, then plus n times n minus 1 factorial all over n minus 1 factorial. Right, so we'll be left with n times n minus 1, then plus n, and that is n squared. And so there you go, the proof is complete. Now let's suppose that a finite set A equals the union of k distinct mutually disjoint subsets A1, A2 through AK. Then n of A is n of A1 plus n of A2 plus so on and so forth plus n of AK, where this n of A denotes the number of elements in A, and this may also be written as the absolute value of A. This represents the cardinality of A, which is just the number of elements that A has. So let's suppose that we are given a finite set A that is the union of k mutually disjoint subsets. If k is equal to 1, then A is the union of a single subset, namely A1. And so A would have to equal A1, and obviously they would have to have the same number of elements. Now suppose that for some integer I greater than or equal to 1, if A is the union from n1 to I of a sub n, then the number of elements in A would be the sum from n equals 1 to I of the number of elements in a sub n. Now suppose that A is equal to the union n equals 1 to I plus 1 of a sub n. What we need to do is show that the number of elements in A is now the sum from n equals 1 to I plus 1 of the number of elements in a sub n. So to do this, let B be the union n equals 1 to I of a sub n. Then A would equal B unioned with AI plus 1. We now show that the intersection of B and A sub I plus 1 is empty. So suppose that there exists an X in this intersection. Then X would have to be in B, but B is this union, so X would have to be in this union. Also, X would have to be in A sub I plus 1. Now, since X is in B, X is in A sub J for some J, right? Has to be in at least one of these A1 through AI. Well, this means then that X is in A sub J and X is in A sub I plus 1. And this means that X would have to be in their intersection. But that intersection is empty. Thus, no such X exists. And so this intersection, B intersected with A sub I plus 1, would have to be the empty set. Thus, we now have that A is the union of 2 mutually disjoint sets, B and A sub I plus 1. And since this set is empty, we have the number of elements in B union with AI plus 1 is the number of elements of B plus the number of elements in AI plus 1. But by the inductive hypothesis, the number of elements in B has to be this sum. So it's this sum plus A sub I plus 1. And by properties of summations, we can now write that as this single summation, which is what was to be shown, and so the proof is complete. And this is known as the addition rule. So the question is, or now the example is, how many 3-digit integers are divisible by 5? All right, so the 3-digit integers. So they are the set of x such that x is between 100 and 999 inclusive. Now, integers are divisible by 5 if the integer ends in 0 or 5. So what we can do is we can split this set of 3-digit integers into 2 mutually disjoint sets. So we can have set A is the set of integers so that 100 less than or equal to x less than or equal to 999, and x ends in 0. We now say B is the set of integers between 100 and 999, and that x ends in a 5. Now, the first digit must be non-zero. So if we say this is the first digit here, it has to be a number between 1 and 9. Right? If it's not, then we don't have a 3-digit integer. Well, here there are 9 choices. The second digit would have to be a number between 0 and 9. Well, that's 10 choices. Finally, this would have to be 0. So we're looking at A first. Well, there's only one choice for that. Thus, the number of element A is equal to 9 times 10 times 1, which is 90. And we can do a similar argument with B, right, just by changing this last part to a 5, but there's still 90. So the number of 3-digit integers divisible by 5 or 0, I'm sorry, divisible by 5 is 90 plus 90, which equals 180. Alright, so we now look at the difference rule. If A is a finite set and B is a subset of A, then the number of elements in B minus A is the number of elements in A minus the number of elements in B. Right, and remember that this set here, B minus A, is the set of all elements that are in B, but not in A. Now recall that earlier in this video, we had shown that there are 1,679,616 pins when repetition of symbols is allowed, and 1,413,720 pins when repetition of symbols is not allowed. How many pins contains at least one repeated symbol? So if we let A be the set of pins such that repetition is allowed, write it this way, and we let B be the set of elements or the set of pins where repetition is not allowed, then what we're looking for is B minus A, right? B is clearly a subset of A. So we're looking for the number of elements in B minus A. So this would be the number of elements in A minus the number of elements in B, right? So it's 1 million. So number of pins with at least one repeated symbol is the number in A, which was 1,679,616, minus the number of elements of B, which was 1,413,720, and this is 265,896. So there's 265,896 pins with at least one repeated symbol. Now, a certain computer access password consists of 3 through 5 uppercase letters chosen from the 26 letters in the Roman alphabet, with repetitions allowed. How many different passwords will have at least one repeated letter? So what we do is we say A will be the set of passwords with repetition. B will be the set of passwords without repetition. Then obviously, just as we did in the previous example, it's going to be the number of elements in A minus the number of elements of B. So we have to determine how many elements are in A. Well, A is the set of passwords with repetition, and the password consists of 3 through 5 symbols. Now, A could then be write it as A sub 3 union with A sub 4 union with A sub 5, right? A sub 3 is the set of 3-letter passwords or 3-symbol passwords. This will be 4-letter and 5-letter. Now, clearly these are disjoint. And now repetition is allowed. So the absolute value, or the number of elements in A, would be the number of elements in A3 plus the number of elements in A4 plus the number of elements in A5. To find the number of elements in A3, this is the multiplication rule, right? You have 3 letters you have to choose, and there's 26 choices for each one. So that would be 26 cubed. Likewise, you'd have 26 to the 4th plus 20, times. No, this is additional, sorry, right? Plus 26 to the 5th. And if you do this out, we get 12,355,928. What's going on? 928. So this is how many passwords are possible with repetition. We can do a similar argument for B. So we'd have B3 plus B4 plus B5. Now here, though, the number of elements in each of these would be different. So we're going to have 26 times 25 times 24 for B3. We'll have 26 times 25 times 24 times 23 for B4. And for B5, 26 times 25 times 24 times 23 times 22. When all the math is said and done there, we get 8,268,000. So then our desired number is their difference, 12,355,928 minus 8,268,000. this gives us 4,087,928. So there are 4,087,928 passwords that have at least one repeated symbol. Now, the addition rule that we studied gives us a way to count elements in a set that is the union of mutually disjoint sets. However, how would we count the number of elements in the union of sets that overlap? For simplicity, we will do our analysis on two sets, but the argument can extend to any number of sets. So to find a formula for the number of elements in A union B, we use this reasoning. N of A gives us the number of elements in A, which would include those that are common elements of B. Likewise, N of B gives us the number of elements in B, which includes the number of elements common in A. So if we were to do N of A plus N of B, right, essentially we're counting the elements common to A twice. So we'd have to take away this double count. That is, we would subtract the number of elements common to A and B, right? So you'd have the number of elements of A and B taken away from N of A plus N of B. And a similar kind of argument can be used if we have three or more sets. Now the following slide gives the rule for two sets and three sets. It can be shown that analogous formulas hold for unions of any finite number of sets. So if A, B, and C are any finite sets, then the number of elements in A union B, so N of A union B, is N of A plus N of B minus N of A and B, A intersected with B, right? And the number of elements N of A union B union C is N of A plus N of B plus N of C, then minus N of A and B, A intersect B, and N of A intersect C, minus N of B intersect C, then plus N of A intersect B intersect C. And we conclude with this example. How many integers from 1 through 1,000 are neither multiples of 3 nor multiples of 5? All right, so for simplicity, let's denote this n to be integers from 1 through 1,000. Then we'll let A be the set of integers, or the set of numbers in n, such that 3 divides it. And we'll say B is that of numbers in n, such that 5 divides it. All right, so we want the elements that are not divisible by 5 nor 3. So what we would have to do is we first have to find the number of integers that's divisible, or the number of elements, so the number of integers 1 through 1,000 divisible by 3. So we want n of A. So how many elements are there in n? Well, there's 1,000, right? There's 1 through 1,000. So if we take the floor of 1,000 over 3, and the floor just simply rounds down to the nearest integer, we get 133. N of B, right? This would be the floor of 1,000 over 5, right? And there's 200. And then finally, N of A intersected with B. So which integers is divisible by both 3 and 5? Well, those would be the integers divisible by 15. So if we do 1,000 divided by 15 and take the floor of that, there are 66 of those. So to determine those that are divisible by neither 3 nor 5, we would take the number of integers in n and subtract out n of a unioned with b, right? So you take away those that are divisible by both 3 and 5. Well, a union b would be, or n is 1,000, minus now a union with b, that would be the number of elements in a, which is 333, plus the number of elements of b, which is 200. Take out those common, that would be 66. This winds up being 1,000 minus 467, which is 533. So there's 533 integers between 1 and 1,000 that's divisible by neither 3 nor 5. All right, and that concludes our initial look at